This is the Earth Science Classroom, a channel devoted to all things Earth science, geoscience, and today we're looking at divergent plate boundaries, or boundary. We're in the plate tectonics playlist, and today I'm going to go through how I draw this plate boundary to my students, how I would do it like a Bob Ross-esque type step-by-step process where I build this huge collage, this huge artistic impression of the plate boundary, and I add in the terms and the scientists and the functionality and how this built into the plate tectonics system, and really starts off the whole kit and caboodle. So this is all about how to draw this boundary, how to explain it in a step-by-step functional way for the students to understand and follow along. All right, so we have this clean canvas, right? A clean whiteboard, smartboard, chalkboard, anything you want to use, you can, all right? Or just bits of paper if you want, all right? So again, like in true Bob Ross fashion, let's just add a nice happy ocean. So here we go. A little happy ocean right here, all right? There we go. So we can add some information at the top there, but we have our ocean, right? And I'm going to add in my ocean floor. All right, here we go. And I'm going to add in my ridge. There we go. We'll get to that later on. And my ocean floor. I've kind of drawn it kind of flat, like a abyssal plain, but as we know from sonar maps from the 60s onwards, that the ocean floor is nothing but flat, has the different landforms and geomorphology as the terrestrial surface does. But for this diagram, I just draw it flat. All right, and I also love where students go, "Oh, look, the Earth is flat," and I just had to, have a little discussion with them about that comment. All right, so here's my crust, and then here is my lithosphere. There we go, very nice. So we can add in different details. So we can add in just in small the crust and lithosphere. Try and draw it small. Even though the students can't always see it, I do kind of repeat it, the words and terms 2 or 3 times as I'm drawing it. I do stop as well. The students need more time to copy things down. I'd walk around, see what they're doing. It's looking correct. Obviously, some drawings will be better than others, but generally you want the main terms. So I have the crust of the lithosphere, and you want to make sure that you include the asthenosphere very clearly. Why? Because it's the depth and layer of the physical Earth where we have the magma generation, the low velocity zone of 150 to 250 kilometers down, which is way down on this map. I always add it in. The asthenosphere obviously is the weak sphere. All right, so it has that plastic behavior with, well, very small amounts, 1 to 5% molten component, which is the magma. So we can put magma down here. Okay, obviously we can add in this crust, and lithosphere is obviously solid, but also it is a thin. All right, and we can also add in right now the composition. So this is going to be salt. All right, and which is the main component. You may get some gabbro, the very base of the ocean crust, but it's mostly going to be composed of basalt. So let's take a little break. Let's go back to our history. All right, so let's go back to 1962. TESC, Princeton University, retired U.S. Navy captain of a boat, now had access to the new technology of sonar, sound navigation and ranging, and he had the ability to map the initial Pacific and Atlantic during the war, World War II, and then use and continue those mappings and the sonar discoveries, finding features like guyotes, undersea seamounts, undersea valleys, abyssal plains, with the sonar. Now, both in the Pacific and the Atlantic, in the middle of the ocean, he found, especially in the Atlantic, he found this. All right. So he found this, and it's also over here. Okay. This is the mid-ocean ridge. It is a raised undersea mountain range that is continuous pretty much the entire way around the Earth, about 70,000 kilometers. It's insane, like a seam on a baseball. So I kind of like introduced it, where it basically goes around the entire Earth as this continuous undersea mountain range. It never pops its head above the ocean. It's not an island. It's all underwater, a few thousand meters down. And this is all rock. It's an undersea volcano or mountain range. And what Hess found when he started to look at this ridge that he discovered, he had the ability to go down and take samples. So if you took a sample of this part here, all right, well, basalt is actually dark gray, but used green. And he found that the basalt was very, very young or very, very new. So it was newly formed young basaltic rock. And it's the same over here too. So the ridge was composed of this young basaltic rock. Now, we know that basalt is our extrusive igneous rock. Extrusive meaning that it is derived or comes from a product of lava, cooling, consolidating, crystallizing lava. Now, you can go back to the rock cycle and mention, the magma to igneous rock formation with crystallization, consolidation, and cooling. And obviously, and you can also go back into the Earth's interior and state that the deeper you go, the hotter temperature, which is the geotherm, the hotter it gets. So as this lava is on the surface, and obviously it's at the bottom of the ocean, which is very cold. All right, so it's a very cold environment down here at the bottom of the ocean. Also, it's without light, it's aphotic. You're going to have this very fast cooling lava that comes out right here in the ridge to produce and cool down and form this brand new basaltic rock. So he, in theory, or basically, found the location of the volcano that is creating this brand new igneous rock called basalt that forms the ocean crust. So if there's lava there, there must be a source of magma that is feeding this lava. Now, it's a very small gap, so only a small amount of lava comes out, but as also under a lot of high pressure. Again, as with the geotherm, the deeper you go into the Earth's interior, the increased PSI, or pounds per square inch, the unit I use for pressure. They can also use other things like millibars and that kind of stuff, but the pressure exponentially increases. So it's like letting air out of a balloon. It comes out real fast. It's going to push its way through. Now, obviously, again, you can link it back to the thinness of the crust being able, the magma is able to push through easier than it would be through a continent which is, 25 miles thick. This is only about 5 to 7 kilometers thick on average. So you have this lava coming out, and it's magma, and this is where the asthenosphere comes back in, is you have these convection currents, which were proposed in the 1930s as existing in the asthenosphere under the crust as a possible way of moving continents as part of the continental drift theory by Wegener. And now this happened after he died. I think it was in 1936, but it was proposed. And then with Hess, find the ridge and find the lava, the convection currents, the uprising or the upwelling of magma was now more substantial. And what happens is some of the magma goes up and creates lava. The The rest of the magma, because it's hitting a solid ceiling in the crust, is being forced away from the ridge, away. So this millions of tons of magma and plastic flow within the asthenosphere is very slowly pushing up, and pulling apart this ocean crust. Okay, and the corresponding product is this side of the ocean floor, the crust is moving this way, left, and this side moving right. So we get what we call a spreading center, which is the location or the point of the divergent plate boundary. Divergent, a divide. Die means to make two. So you are splitting into two, and vergent means, verge means to move. So you're moving these two bits in opposite directions. And usually in front of the class, I would have, next to this title, I would have just the arrows like that, just to symbolize that the plates are moving away from each other, okay? And the convection currents are the mechanism, or is the mechanism that is moving this. Now, as the ridge is built up, we will also have a lovely thing called, I'll do it in blue, lovely force that's applied, force of attraction, which is big G, gravity. So what happens is once the lava cools and forms salted rock, the gravity takes hold and is going to push down on the ridge, which is elevated, and this is called ridge push. Oh, no, ridge push. Pushing by gravity down, so that also would aid the movement of the plates to diverge and then go further away. Now, further evidence that the ocean floor is moving. Don't forget, Hess was only the first one, or first of a few scientists to establish that the ocean floor can actually move. Before that, before the 60s, scientists were, didn't have any clue that the ocean floor was moving. Why? Because it was hidden under an ocean that was very deep and very hard to examine with experiments. So he also took samples of rock further away from the ridge, and what he found was the further away, or the greater the distance, or the increase in distance, the older the rocks get, the basalt. And what we found was in most ocean basins, the ocean crust only gets to about, maximum of 180 million years old. And you're like, well, that's pretty old. But, okay, if we compare it, so this is like the Pacific. On the western side of the Pacific, near the Asian continent, the ocean crust basalt is around 108 million years old. If we compare that to the continental crust and the average age of the continents being in the billions, we see a vast difference between the age of the ocean floor and the age of the continents, meaning the continents have been very stable, very consistent over the Earth's history, over billions of years, whereas the ocean crust is always constantly moving and constantly being born, and there must be a way that the ocean floors are destroyed at the edge, really far away from the ridge. So the ridge is where the plates are born, or this is why we call this a constructive plate boundary, or PB. So a divergent plate boundary is a constructive plate boundary. It's where we make the new ocean crust, the new basalt. And it slowly moves between 5 to 10 centimeters per year. It's moved by the convection currents. And again, the Pacific Ocean is the fastest, between like 10 to 11 centimeters per year. Atlantic Ocean is like 6 to 7. Indian Ocean, again, is kind of the same as the Atlantic. But what we're finding is evidence is starting to stack up that the ocean floors are moving. Okay, and we can also look at the paleomagnetism, the stripes, right? So I'm just do some stripes here, stripes of normal polarity versus reverse polarity, and they are symmetrical, so they're both the same on both sides of the ridge. And we can also measure and see the change in polarity of the Earth hidden in the magnetite, in the iron, in the basalt, that shows the polarity when the, so I'll just do, here we go, normal polarity right now. There we are, so either side normal. So as it moves, you get this striped zebra crossing type formation of paleomagnetism set in the rocks from when they were formed in the lava at the ridge. Again, more compelling evidence the ocean floor is moving. And now with satellites and GPS, we can actually see exactly where the ocean floors are moving, how fast they're going, and predict the future outcome of oceans and tectonics. So again, I build up from very simple, I add in the details, I add in the history, the scientists, where it came from, add in the evidence, and make sure you focus on the convection currents, because that's the mechanism, and you focus on the direction of movement and why the ridge was so important for opening the discovery gates of plate tectonics, because this is where they're born, and this starts the whole cycle off, and also led Wilson, oh no, Wilson in 1966 to generate his cycle on basically rifting and production of ocean basins. All right, hope this helped out. And any questions, leave a comment. And hopefully you guys subscribe for more videos about geoscience.